Hello. Today we're talking about Rust-Lang collections. Rust is a modern systems-level programming language designed to provide high performance, memory safety, and concurrency without sacrificing ease of use. I talk more about how great Rust is in this video. One of Rust's standout features is its rich collection of collection types, designed to provide efficient and safe ways to manage and organize data. Whether you're building systems, software, web applications, or game engines, organizing and manipulating data is a fundamental part of programming. Rust collections empower developers with flexibility and control, ensuring that data handling is not only performant, but also free of common bugs like data races or memory corruption. Rust collections are more than just data structures. They're building blocks of crafting solutions that prioritize both speed and reliability. I'd like to start by mentioning the compound types, tuples and arrays, as I consider them baby collections. They're stored on the stack as their size and type are fixed at compile time. Tuples group multiple values of different types into one structure. They have fixed size, meaning once created, the number of elements and their types can't be changed. You can combine values of different types, so it's like a structure, but without naming the fields. To access the elements, you rely on their position and state, the index, which can make the code harder to read for complex data. Tuples are lightweight, which is perfect for quick bundling of related values. The use cases would be returning multiple values from a function and temporary grouping of different data types. Arrays are collections of elements of the same type with a fixed size known at compile time. Next, I'd like to mention strings briefly. The Rust book puts them in the common collection section along with vector and HashMap because of its behavior and usage, but in my head, string lives separately somehow. In Rust, string is a collection specifically designed for handling text. A string is an owned, mutable, and dynamically sized collection of UTF-8 encoded text. It's built on a vector of U8 internally, so it has similar memory and performance characteristics. String grows and shrinks as needed, allocating memory on the heap. It offers many useful methods for text manipulation, such as push, pop, replace, and split. If you want to have a better understanding of how string works, the Rust book is there for you, as well as the informative video on Let's Get Rusty channel. Collections. It says here that vector and HashMap are the universal collections, but there are 8 types of standard library collections, and my task for today is to show you how they're different, to give you the high overview so you'd know which one to use in this or that situation. And then you'll dig deeper on it in the docs by yourself if needed. So all of the collections types are grouped into 4 major categories: sequences, maps, sets, and BinaryHeap is there all alone in the last one. Let's get it started. Vector is a dynamic array that grows or shrinks at runtime. It's like a magic drawer that grows as you add items. If it runs out of space, it moves to a bigger drawer, but the move takes some effort. VecDeque is a double-ended queue that supports efficient insertion and removal at both ends. Picture a queue at a theme park where people can enter or leave from both ends. Or, for example, VIP entry at the front or an impatient person leaving from the back. LinkedList is a doubly linked list where elements are linked via pointers. Imagine a chain of paper clips where each clip knows where the next one is, but finding a specific clip requires going through the chain. HashMap is a key-value store with hash-based indexing. It's like a filing cabinet with folders labeled by hash codes. You can quickly find the right folder by its label. BTreeMap is a key-value store with sorted keys using a B-tree structure, like a library bookshelf where books keys are stored alphabetically, making it easy to find books in a specific range. HashSet is a collection of unique values using a HashMap internally, like a guest list at a party where each name is unique, ensuring no duplicate entries. BTreeSet is a sorted collection of unique values using a B-tree, like a sorted guest list where names are unique and arranged alphabetically. BinaryHeap is a priority queue implemented as a binary heap, kind of like a priority queue at an airport where passengers are boarded based on their ticket class, with the highest priority person served first. It all might be confusing to remember as there are many types of the collections, so I put what I've just talked about in this table to compare the collections. And then I wanted to simplify this info even more, so I decided to give a character to each collection type, as I had this association with the Pokemon's evolution process. So there's a card with the collection type functionality, which should be really useful for better understanding, and its place in the evolution chart. I've changed the classification a bit according to my understanding and vision, and I hope you perceive this as entertainment in case you disagree with the changes. Sequence collections, dynamic ordering evolution. Baby Charmander or array. The smallest and simplest form of collection, a fiery little bundle that holds a fixed number of elements on the stack. It's predictable and reliable, but doesn't grow or change size. The use cases for it storing a small fixed numbers of elements like RGB colors values or the months. Low-level programming where performance and predictability are critical. The next one, Charmander or vector. The array evolves into a vector, gaining the ability to dynamically resize. Now fueled by the heap, this form is flexible and capable of handling changing data sizes. Like Charmander, it adapts to bigger challenges. The use case for it, storing a dynamic list of user inputs or configuration options. Charmeleon or LinkedList. With this evolution, the collection gains new powers, the ability to efficiently insert and remove elements anywhere. Like Charmeleon, it prefers to stay agile, focusing on dynamic movements rather than direct attacks like random access. The use case is when frequent insertion and deletions occur and random access is unnecessary. Charizard, VecDeque. The ultimate form of sequences, combining the flexibility of vector with the efficiency of linked list at both ends. It soars above the others, offering versatility for double-ended queues. The use case is implementing first-in, first-out queues or buffers. Maps, key-value evolution. Bulbasaur or BinaryHeap. Not quite a map yet, but the starting form of ordered storage. BinaryHeap keeps elements organized by priority rather than by the key. making it a budding helper for tasks like scheduling or rent list. A partially ordered structure that doesn't store key-value pairs directly, but helps introduce the idea of ordered data. The use case is implementing task schedules or tasks where only the highest or lowest value matters. IVSOR or HashMap. BinaryHeap evolves into HashMap, gaining the power to associate keys with values. It's fast and efficient, like IVSOR, moving through dense foliage. However, it doesn't keep things in order, just pure speed. The use case is storing a mapping of usernames to user data. VenueSOR or BTreeMap. The final form of maps, BTreeMap combines key-value pairing with natural order, towering over the rest by keeping elements sorted. Like VenueSOR, it balances power and precision. The use case is indexing data where order matters, like ranges of IP addresses. Sets or uniqueness evolution. Squirtle or HashSet. The starting form of sets, HashSet, is all about enforcing uniqueness without worrying about order. Like Squirtle, it's quick, efficient, and straightforward in its approach. The use case is checking for duplicate values in a list. VarTotal or BTreeSet. Evolving from HashSet, BTreeSet brings order into the mix. Like VarTotal, with its enhanced agility and accuracy, this form organizes unique elements while still ensuring no duplicates sneak in. The use case is handling sorted unique data like leaderboard scores. It was fun, wasn't it? So far, I've presented the two classifications, the one from the Rust book and my own. Get ready for the third one. Rust Standard Library 8 collections can be divided in the two groups: value-only collections like Vector, VecDeque, LinkedList, BinaryHeap, HashSet, and BTreeSet, and key-value collections, HashMap and BTreeMap. And this inspired me to create another chart to help you figure out the right collection for your needs. Here we go. The decision process starts by asking whether you need a value-only or key-value collection. If you need a key-value collection, the choice is straightforward. Unordered, HashMap. Ordered, you go with BTreeMap with uniqueness enforced for keys. If you need a value-only collection, the options expand. Should the collection be ordered? If no, use HashSet for unique unordered values. If partially ordered, use BinaryHeap for prioritized access, which gives you an arbitrary order but with either minimum or maximum priority group at the top and no uniqueness. If yes, in case with the ordered list, you get to choose between sorted, BTreeSet with uniqueness as a bonus, and unsorted values, where you get to consider the operations. If you mostly add or remove from the ends, use VecDeque. If you mostly add and remove in the middle, use LinkedList. Otherwise, use Vector for general purpose storage. Do you agree with me that this chart deserves a like and maybe even a comment? Working with collections requires to use iteration, which is the process of accessing each element in a collection one at a time in a specific order. It's a fundamental programming concept because it allows you to process, transform, and interact with collections without needing to manually manage the details of indexing or traversal. For example, printing all items in a list, filtering items that meet a specific condition, or transforming data into a new format. Iteration is important because it simplifies code. Instead of Manually managing loops and indices, iterators handle the complexity for you. This leads to cleaner and more readable code. Versatile, iterators can be combined with powerful methods like map, filter, and fold to perform complex transformations concisely. These methods are composable, enabling expressive and functional style programming. Efficient. Rust's iterators are zero-cost abstractions. They don't add runtime overhead compared to manually looping through collections. Laziness ensures computations happen only when needed. Safe and reliable. Iterators help to prevent common bugs like out-of-bounds errors since they abstract away their underlying indexing. There are three types of iteration through collections in Rust. Consuming iteration or inter-iter. The collection is consumed, meaning you no longer own it after iteration. Borrowing iteration or iter. You borrow each element without taking ownership, so the collection remains usable. And mutable borrowing iteration or iter-mute. You borrow each element mutably, allowing modification in place. But iterators aren't just for looping. They come with powerful methods to process collections. Let's take a look at some of them. All checks if all elements satisfy a condition. Method any checks if any element satisfies a condition, quickly tests conditions on collections. Chain combines two iterators into one when you want to concatenate collections. Cycle repeats the iterator endlessly, useful for infinite sequences or periodic data. Enumerate adds an index to the items in an iterator when you need both the item and its position in a collection. Filter keeps only items that satisfy a condition. Find finds the first element that matches a condition, provides quick access to specific items. Flatten flattens an iterator of iterators into a single iterator for when working with nested structures like vector of t. Fold combines all elements into a single value. Inspect runs a closure on each item without consuming the iterator, useful for debugging or side effects during iteration. Map applies a function to each item. Partition splits items into two groups based on a predicate, useful for separating items into categories. Method pickable allows you to look at the next item in the iterator without consuming it, for the cases when you need to make decisions based on upcoming items. Rev reverses the direction of iteration when you need to iterate a collection backward. Method skip skips the first n items in the iterator when you want to ignore some items before starting iteration. Take limits the number of items returned by the iterator when you only need the first n items. Zip combines two iterators into a single iterator of tuples, thus parallel iteration over two collections. As you might have noticed, there are many more iterator methods listed in the documentation. Take some time to look through them, as you'll definitely be using some of them, and it's good to know the range you're choosing from. I hope this video was useful for you. Thanks for watching. Bye!